Hello everyone, my name is Ruphan and I'm glad to present my work on multiphysics simulation of magnetically actuated robotic origami worms. In recent days, origami robots have shown promising results in various fields ranging from medicine to space engineering. It is important to minimize the size and weight of these robots in certain applications such as biomedical robots used for minimally invasive surgeries. Magnetic actuation of such robots can reduce their size by eliminating the need for any circuitry involved and help in waterproofing and removing battery hazards in such critical environments. One caveat of magnetic actuation is the complexity of control involved, which has motivated us to develop this multiphysics simulation. Grasshopper 3D is a visual programming tool that has been used to design the origami robot under consideration. The image shows the workspace of the simulation tool, which uses Kangaroo, a physics engine, to achieve realistic results. Such a simulation can help in design parameter optimization, predicting the robot's performance, implementing control algorithms for actuation, and synthetic data generation. The simulation solves multiple goals iteratively in the presence of various constraints. The goals involved here are to model the following: internal and external permanent magnet interactions, origami geometry, gravitation and frictional force, and the folding in each crease. Magnetic dipoles are the fundamental components in magnetostatics. However, unlike electrostatics, where an electric dipole is made up of a positive and negative charge, no evidence has been found for magnetic charges. Still, previous studies have shown that using an imaginary set of equally positive and negative magnetic charges separated by a distance is effective in modeling a magnetic dipole. Figure A shows such a setup of a magnetic dipole. The magnetic dipole moment of the dipole is calculated analogously to an electric dipole as shown in equation 1. These hypothetical magnetic charges, being analogous to electric charges, follow Coulomb's inverse square law. Using this, forces acting on a dipole or any magnetic charge can be calculated. Figure B shows a setup of two dipoles exerting a force on each other. There are a total of 4 magnetic charges, and each one of them experiences a force due to the other magnetic charges. We neglect the force between the magnetic charges of the same dipole, as the force is nullified by the internal forces that keep the dipole length constant. We have a total of 8 different forces, 2 on each magnetic charge. The net force on the dipole M1 can be computed by the vector sum of the 4 different forces acting on it. A generalized formula for the forces experienced by the ith dipole in a setup of n magnetic dipoles is shown in equation 2. Previous studies have shown that a magnet of any shape can be constructed by populating it with dipoles uniformly and aligning it according to the direction of the magnetic axis. Figure A shows this by using just 4 dipoles to construct a simple bar magnet. However, the density of dipoles is very low here, which leads to poor results of the magnetic field surrounding the bar magnet. However, the magnetic field far away still remains accurate. Thus, it is important to fix the dipole density according to the closest distance of approach and the computational complexity involved. We found that 64 dipoles per centimeter cube to be the most effective value in our simulation. More than that affects real-time simulation, and less than that affects the accuracy at closer magnet proximity. It is a common and effective approximation to consider the individual origami facets to be rigid to increase the speed of simulation exponentially. In our case, this approximation turns out to be very effective due to the presence of a very large number of creases to allow bending almost anywhere in the origami. Thus, the bending of individual or triangular facets in our origami is neglected. The image shows the setup of a step-by-step process of constructing the origami. The first part of the image shows the primary component of our origami worm tessellation that repeats itself. This is bent to obtain the prism-like structure as shown. The slant lines are assigned as mountain folds and the straight lines as valley folds. Folding using this gives the next image, which we call the primary component of our origami worm. We then attach n such primary components to obtain the entire worm, where n is 12. Then we attach 3 disc magnets to act as internal permanent magnets at the head end, center, and the tail end. The orientation of these magnets is fixed in such a way to obtain a stable motion pattern. 3 different translation motions are obtained, namely the peristaltic motion, omega motion, and inchworm motion. Each of them has its own advantage in considering the navigation space and contact friction during locomotion. The video snippets shown below show all the 3 different motions. Here is a detailed analysis of how different motions happen by just changing the orientation of the external permanent magnet. The peristaltic motion happens when the compression occurs in the front end due to the north poles of the front end disk magnets getting attracted by the south pole of the external magnet. When the magnet is taken far, the expansion occurring in the origami makes it move forward. The omega motion is obtained by rotating the external magnet by 90 degrees to magnetically lock the origami and external magnet ends and brought closer. The inchworm motion is facilitated by flipping the magnet in comparison with the peristaltic motion. The internal magnet at the center plays a major role here by rotating counterclockwise to create the hook-shaped shield. The simulation has several constants to be fixed to obtain the realistic dynamics as seen in the real origami. These constants are estimated by performing multiple experiments on the real and simulated setup of the origami. The hinge stiffness of the origami is the most important parameter as it dictates the amount of bending in the origami. We set up a compression and 3-point flexure test to obtain the force deformation curves of the real origami as shown in the figure. This is then repeated in the simulation, and the hinge stiffness is adjusted up until the force deformation curves closely match with the one obtained earlier. Interestingly, we found that the hinge stiffness constants obtained from the compression and 3-point tests were very close. This means our hinge model is a very good approximation for various degrees of bending. Similarly, the real force distance curves between two N52 neodymium magnets were fitted in simulation to estimate the dipole strength of the magnets. The initial value of the folding was estimated by measuring the length of the origami and using cosine rule to get the angles. A slope sliding test helped to estimate the coefficient of static friction. After fixing all the unknown simulation constants, we evaluated the simulation using another set of experiments. Firstly, a force test was done by tying the origami to a string, which is connected to a measuring device. During the origami actuation cycle, the force curves for all three different motions were plotted and were found to resemble closely. The setup and force curves are shown below. Next, we performed the displacement and deformation test. The center of the origami was tracked to plot the displacement curve for the origami. The origami was split into 5 equal sections and colored blue, pink, white, green, and red to track the deformation as shown. The distance between the centers of adjacent colors was monitored using a color tracker. In the absence of any deformation, the deformation ratio is 1. The deformation ratio is the ratio of the current distance between two sections and the initial distance between the two sections. When a section compresses, the ratio goes below 1, and when it expands, the ratio goes above 1. It was found that these curves also have a resemblance as shown below. The red curves are from real experiments and the blue are from simulated experiments. Since the simulation is calibrated and evaluated using practical experiments, we use it to do difficult and impractical experiments in real life. One such example is a strain test during the origami actuation. This isn't easy to perform practically. However, it is simple to monitor in the simulation. This helps to identify the parts of the origami undergoing high stress to identify suitable materials to construct the origami. Another such example is origami geometry optimization. The worm could be made with a larger number of segments or different heights to base ratio of the primary triangles involved. This parameter search in real life means making the origami for each possibility to test its stability. However, in simulation, it's quite simple and effective. So we showed a demonstration of our multiphysics simulation that is the first work to show a realistic simulation of magnetically actuated origami worm robots. We used a set of internal and external magnets to deform and steer the robot according to our requirements. We set up several practical and simulation experiments to calibrate and evaluate the performance of a simulation and achieve good results. The key takeaway of this work is to use the simulation to do things that are impractical in the real world. Future works can target these areas to build upon this work. A few possibilities of extensions are to make a robust control algorithm for more sophisticated actuation. We used a simple sinusoidal periodic motion to achieve basic deformations. More complex motions can be achieved using varying orientations and magnet trajectories. Multiple external magnets could also be used to achieve even more sophisticated actuation. Another great advantage is to use the simulation to generate robotic perception datasets. Deep neural networks are becoming more and more data hungry, and it's impractical to collect and label huge data sets manually. This simulation capabilities can be leveraged to do this with ease. The video also shows that we can extend the simulation to different origami and not restrict it to just worm robots. The water bomb origami is magnetized at different nodes, and it's deformed using by translating the external permanent magnet as shown. Thank you for your patient hearing. You may send your questions, if any, to the mail ID shown for further clarifications.